So, hello everyone. It's a pleasure to have Khaled Said here today. Thanks a lot for accepting our invitation. Khaled completed his PhD in 2017 at University of Cape Town, working on peculiar flow fields in the zone of avoidance. After that, was a postdoc at the Australian National University for 3 years, and then he moved to the University of Queensland, where he is currently a research fellow in cosmology gravitational waves. Khaled has been working on large structure and cosmic flows. He measures peculiar velocity for galaxies, directly using distance indicators or indirectly using reconstruction techniques. Today, he will present DESI peculiar velocity survey, fundamental plane. Khaled, please, you can start when you're ready.
Thank you very much, Eleonora, and thanks everyone for being here. So it's really a pleasure to be part of this CosmoVerse seminar. So before starting, I would like to mention two things. First, I would like to thank all our sponsors and the 72 participating institutions in DESI. And the second thing is that while I will be talking today about mainly H0 and distance measurements using distance indicators, the main goal of DESI BQA velocity survey is actually to get to the BQA velocities. But as you will see in the coming slides, to do this using distance indicators, you have to go through distances first. And if you measuring distances, like through distances, and you have already the redshift, the first thing that comes to mind will be to measure the Hubble constant. Yeah. So first, what are these velocities? They are actually if you look at any galaxy on the sky, they have two components of velocities. The first one is expansion velocity, which is always away from us. And the second one is the BQA velocity, which is basically the deviation of from this smooth Hubble flow. So this equation shows that nicely. So on the here you see this is the redshift, and this you can divide this redshift into two components: z bar, which is a cosmological redshift corresponding to your true distance. And again, this is always away from us because of the expansion of the universe. And then you have the P, which is your BQA velocity. And again, this is a deviation of this smooth Hubble expansion. So how do we actually measure the BQA velocities? So to do this directly, individually, galaxy by galaxy, you have to use something called distance indicators. And we have, as you all know, we have a primary distance indicators, such as parallax, masers, megamasers, and gravitational waves. But for parallax, you cannot go far. With this, for masers, you only have a handful of these measurements. And for gravitational waves, you have only one galaxy. So if you want to measure hundreds or 1,000 of galaxies, you have to go through secondary distance indicators, such as type 1e supernovae, Tully-Fisher relation, or fundamental plane relation. But the disadvantage of these secondary distance indicators is that they need to be calibrated using one of the primary distance indicators, basically. So you have to build what's called distance ladder to be able to get the absolute distance from Tully-Fisher or fundamental plane, etc. Okay, so I'm giving here an example of how we, in brackets, how do we measure distances from Tully-Fisher relation. And I am giving an example in Tully-Fisher relation first because I love Tully-Fisher relation because it's it's a 2D, it's a very easy linear relation. There is no hidden parameters, no little h, nothing in there. So it's really easy to understand. So you can write the Tully-Fisher relation into this form, where m here is your absolute magnitude and v max is your maximum rotation velocity. Some people use the flat part of your rotation curve. Some people use the maximum of your rotation curve, but it's really it doesn't make a big difference here. It might make a difference like in the scatter, in the intrinsic scatter of the relation, but like for our purpose here, it doesn't make any difference. So first, you need to calibrate this relation. So you need a subset of your sample that have absolute distances. And again, that comes from primary distance indicators. So here you have luminosity, which you can construct using apparent magnitude and the distance, the true distance. And then you have a rotation. And your rotation doesn't depend on distance or redshift or anything. This is actually a distance independent parameter, your rotation curve or your rotation velocity. But your absolute magnitude, you need distance to be able to construct the luminosity. So once you have luminosity and rotation, you can just plot them against each other, and you will end up with like a very nice correlation here. So the next step is just to fit a straight line, like, and see this correlation. And that's what we do in here. So once we have this straight line, so we call this the absolute calibration or the template relation. There is so many names for it, but that will be your actually your calibrated relation. And you can use this relation here in the third plot, given a rotation. So you can get a rotation for any galaxy. And once you have the rotation, you can just read off the luminosity out of this relation. Like just like go to like a radio telescope or get a spectra and like get a rotation curve or the width of like the H1 profile, and you will have the rotation. And that again doesn't depend on redshift, doesn't depend on distance, doesn't depend on anything. And then you will be able to read off the luminosity. Once you read off the luminosity, you can compare your luminosity with apparent magnitude using distance modulus, and you can get your true distance for any number of galaxy you have. So to calibrate the relation, you don't need thousands of galaxy, like 100 galaxy or even less than this is acceptable. And you can use this relation to measure the distance for like many thousands of galaxies. Okay, so like now we know how this works. Okay, what is actually DESI peak loss survey? I'm sure like most of you know what DESI is, and DESI is like this cosmological survey with amazing instrument that will do like many things. But like peak velocity wasn't actually a part of DESI when DESI started. And it was only like by the end of 2020 when the DESI peak velocity was being accepted, the proposal was accepted to be a secondary target program. And but that program was very successful, and now we think that program will be the largest collection of distance measurements of nearby galaxy ever assembled, and like that will enable like a huge range of science. And just to put this into context, so the DESI will give you this like the sample that DESI will give you is at least 4 times all the peak velocity ever measured, like collected. So if you collect all the peak velocity that has been measured together and combine them in one survey, DESI will be 4 times larger than this. So it's really amazing instrument, and the density of fibers in the focal plane is huge that enabled us like to get many measurements at the same time. So during SV only, during the science verification only, we already have 3 papers from these data. So the first one that was led by Christoph Solder, that's about the target selection. And we show in this paper, we show how we select our sample, both both fundamental plane and Tully-Fisher. And we also give some Fisher forecast for some of the cosmological parameters. So the second paper is a Tully-Fisher relation. So first, the target selection paper has been like accepted and published, and you can find it on our archive already. the Tully-Fisher relation that's led by Kelly Douglas from Rochester. And the interesting thing about this Tully-Fisher relation from DESI is we're using fibers spaced on the major axis of the galaxy to be able to measure the rotation curve. So people have either used H1, like double horn profile, or constructed the full rotation map using bundles of fibers, tens of fibers basically, or they used the long slit to be able to do this. But we're using like fibers spaced along the major axis to do this. And in some cases, we're using only 2 fibers to do this, which is actually amazing if you think about it. And that paper is actually in collaboration wide review now, and it should be on archive like very soon. And the third paper is the fundamental plane, and that will be like my focus in this talk. Okay. So like fundamental plane is basically the same as Tully-Fisher. So you need some parameters that doesn't depend on distance. And in our cases, this is the velocity dispersion. And this is the velocity dispersion of the stars inside the galaxy. This is not to be confused with the velocity dispersion of the galaxy in a cluster. So this is basically the stellar velocity dispersion of the elliptical galaxy. And this is a surface brightness profile. And these 2 parameters, this is coming from photometry, this is coming from spectroscopy, and these 2 parameters, they are like basically distance independent. And what I mean by distance independent here is like you don't need distance to be able to measure these. And the third parameter is actually our desired parameter, which is like the effective radius. So we use velocity dispersion and surface brightness profile to predict RE. And then once you predict RE, you can, the same as the Tully-Fisher, but instead of absolute magnitude and apparent magnitude, here we're comparing physical radius with angular radius. So angular radius is coming directly from photometry. And if you compare physical radius with angular radius, you can get the distance, dA, which is the angular diameter distance in our case. Okay, so now, so like during SV, we actually selected our sample to basically answer like a few questions. And the first question was like, would the desired signal to noise ratio be achievable from the DESI spectrum? So basically the question that we are asking, will the spectra give us a good velocity dispersion without a huge uncertainty, so it doesn't dominate the error budget in this relation? So we calculate the error budget. You can think of the error budget like this. We calculate it actually. We use a different method to calculate it, but this is a simple way to think about it. So we have the total error in the R direction, and remember, like the fundamental plane is a 3D plane. It's not just a linear relation like the Tully-Fisher. It's a 3D. So, but the error in distance correlate very well with the error in the R direction. So you can calculate this error in the R direction using you can add all the errors in quadrature using epsilon s, which is the error on your velocity dispersion. And this is all the error coming from photometry. That includes IE and include sigma E, which is the angular diameter distance, plus some intrinsic scatter like in the relation itself. So now, so like the fundamental plane has an intrinsic scatter of 20% already in distance. So like we don't want to increase this anymore. But if your error in the velocity dispersion exceeds the 20%, that means it will start to dominate your error. So the first thing that we did, we measured the velocity dispersion ourselves using PBXF. And the way that we did this is by actually comparing it with like some templates. And in that case, our template is coming from a library called NWS. And as you see here in this plot, so at least 75% of all our galaxy have a relative error less than 10%. And on the y-axis here, we have the signal to noise. And as you see, you don't need a huge signal to noise to be able to do this, which is actually great. So at least 75 our sample have error of 10%. That means the error in velocity dispersion will not be a problem for us to do the fundamental plane, or in other words, so it will not take the error in the fundamental plane farther than like the 20% that's already in the intrinsic scatter. That was the first question, basically. The second question is, like, do we have any systematic offset in our sample? So like, do we have a plate-to-plate offset or tile-to-tile offset? So basically, we, instead of taking the full depths of our spectra, we take the bare tile spectra. So we have the same target that has been observed like many, many times. We don't stack them, we compare them. So to see if the same target has been observed twice, do we get the same results or do we get a different result? Because if we get a different results, that will be like a source of systematics. And if we don't know what that is, we cannot correct for. And that will be bad when it comes to cosmology, actually. So we divided our, like, if the spectra has a higher signal to noise, we call it primary. And if it has a low signal to noise, we call it secondary. And we compare both of them together. And you can see the comparison here. Here's a one-to-one comparison. And you see the agree within the uncertainty. And here is another way to look at this comparison, which is a difference versus the mean. But the most important thing here is the relative error, actually. And for the relative error, you need this relation, you need to be Gaussian, centered on 0, with a standard deviation that's 1. And that looks like that's exactly what we found. And so the distribution of our relative error is a red histogram here. And the white solid curve is not a fit. This is just a Gaussian overplotted on this distribution. It's a Gaussian centered on 0 with a standard deviation of 1. And you can see it agrees very well. And with that, we take that, like we said, okay, our sample, we don't have any internal systematics. We can move on like to the next check. And the next check was actually external consistency. And we compared with many, many surveys. So like, but like basically the best surveys like currently available is SDSS. So we compared with many surveys, but we're showing here only like the SDSS comparison because that's basically the survey with many repeat observation or observation that's also observed with DESI. So we compared SDSS pipeline measurement of the velocity dispersion with the DESI, which what you see in the top panel here. And we compared another measurement that used SDSS, but used a method that's comparable to our method, which PBXF. And that's called SDSS Portsmouth. That's coming from the Portsmouth group. And we compared both of them. And you can see with the pipeline, there is a shift here. And for the Portsmouth group, there is a shift on the other side. So what we concluded from this is that DESI actually agree with both SDSS pipeline and SDSS PBXF more than SDSS agree with themselves. So like, I know this is not the best conclusion, but we said, okay, there is nothing that we can do about this, but we'll add this as a source of systematic every time we try to do like to measure in cosmology. So basically we propagate this as an error like all the way until like our H0 measurement or F sigma 8 measurements. Okay, so now moving to some results, and what you see here is actually that's the Hubble diagram, but that's a different kind of Hubble diagram. You usually see a Hubble diagram using luminosity distance, but what you see here is the angular diameter distance. And so like this equation is little bit different from what's in the paper actually, because in the paper we had like we used the wrong equation, but it doesn't make a big difference. It's like the difference like 0.05% like on each node. So like it's a very small, a tiny difference. And the difference is actually we took the Taylor expansion of the luminosity distance and then divided by 1 plus z square. So, but that's not the same as taking the Taylor expansion of the luminosity distance divided by 1 plus z square. So basically, when we took the Taylor expansion, we took the Taylor expansion of the luminosity distance, not of the angular distance. But we corrected this now, and again, so like the error is like very small. It's tiny. So this is using 4,000 fundamental plane galaxies. The redshift range is between 0.01 and 0.1. And for the 0-point calibration, we use the surface brightness fluctuation in the coma cluster. And we used like only one galaxy here. But we like, again, so this is not the best we can do, but we were trying to do during SV, we're trying to streamline the whole process to prepare for year one data. So for year one data, we'll have many clusters, many SPF that's anchored to TRGB or anchored like to Cepheids, and we'll try to do both sides. So, but for this one, like we're using only one galaxy in coma, one SPF galaxy in coma to do our 0-point calibration. So because our redshift range is very small, like basically it's going only to 0.1, so we fix it Q naught and J naught, and we fit for Hubble constant. And when we fit for Hubble constant, we do additional H naught cut to limit the effect of peak velocity. And that's what we found. So we found an H naught of 76.05, which is a little bit high, like, but because we're using only one galaxy to do the calibration, our statistical due-to calibration is huge. So actually this measurements agrees with basically with shoes, and it agrees with even with Planck within 2 sigma. So, but this number will go like will be very small, like in year one data. And basically in year one data also our statistical will be like much smaller than this, because this is using 4,000. Our year one will be 100,000 galaxies. So that will be very small. And we might be able to reduce systematic, but because of the huge number, so we might be able to divide our sample into subsets and do more tests, but we're still doing this at the moment. Okay, so what happened like if we, instead of fixing Q naught and J naught to like basically omega m and omega lambda to 0.7, 0.3 and 0.7, and instead take the values from Planck for omega m and omega lambda, and we see no change at all. So that's what like this purple curve gives you. So if we use Planck's value for omega m and omega lambda, we still get the same H naught, which is like 76. But basically, this is a curve if you use Planck's value for H naught, omega m, and omega lambda, and you see shift. Yeah. And if you look at our residuals, so like you see, it's going up and going down here, basically. And at the beginning, we thought, okay, what's going on here? Is that a volumetric effect? Is there like we didn't correct for Malmquist bias correctly? So we did all the check, and because we did all these corrections, so we said, okay, it might be a large scale structure, and we checked with the reconstruction. So we got like the peak velocity from the three reconstructions. So the first one is 2m++ using SDSS and 6CDF, and that's from my paper in 2020. And then we used 2mRS from Lelo and Nosser in 2021. And we even used an older model, which is a 2m++ from Carrick 2015. And what we see here is actually like this is actually an attractor. So like what you see here is like galaxy are like going toward an attractor, falling into an attractor, and there is a backside infall from the other side. That's why you see going up and down here. Okay, and we did a lot of systematic check. So the first thing, so like our analysis using SPF is this cyan curve here, and then our analysis using TRGB is our dotted white line, and you can see basically that's the huge difference between like if you compare with other sources of systematics. So we tested also like what if we include spirals in our sample. So like intentionally like have spiral galaxy into our sample, and our sample is supposed to be elliptical and clean. So, and what happened for this is actually a very small effect here. So, but we did another check of like, what if we exclude spirals from our fundamental plane, like fit the calibration and the Hubble diagram, but using visual inspection. And that one was a huge effect. But we decided not to add this as a source of systematic because we find that like by doing visual inspection, what we actually doing is we introducing a, a source of systematic, because we found that our visual inspection correlates with the size of the galaxy. And that's really bad. So like basically you have a cut of your sample based on size, and that's not included in our selection function that we're correcting for later on. So we didn't include this yellow, but we have it in the paper, just like not to do any visual inspection in the future. So we're correcting, so like you remember when I said like our velocity dispersion doesn't agree very well with SDSS. So we actually tested for this. What if we move all our DESI velocity dispersion to SDSS? So calibrate DESI to SDSS and get the same results, and the effect is tiny, it's very small. So what if we don't do any redshift cut at all? Like, so we cutting at redshift 0.023 to actually 2, not 23, 0.02. So like to avoid the huge effect of peak velocity, and that moves it down a little bit here with this curve. So, and what happens if we have a higher redshift cut? So like if we cut instead of 0.02, we cut at 0.034, for example, and we have this other curve here. So like basically if we have no cut, it moves, it becomes lower. If we have a higher cut at redshift, we get a higher value of H naught. So, and we also tested applying a BQ velocity correction for our ZCMB when we're fitting for Hubble constant, and that moves it a little bit high as well. Okay, so like after we put this paper on archive, Dan Skolnick and Adam Rees actually published this very nice paper, which is basically saying DESI like moving our Hubble tension to our own backyard. And like I love this paper because it's a very simple, like it has a very simple idea and it puts it all clear. So, and basically what they did is they used this equation here. So they said like they took our H naught value and they took the distance to coma that we used for calibration, and they said, okay, if we substitute Planck's value for H naught here, if we use Planck's value, what value of what distance to coma that Planck's will give? And they found that Planck will give a value of higher than 110 megaparsecs. And they compare that with like many measurements from like many surveys and from the literature as well. And they did their own measurement like in coma using supernovae. And it looked like that it's unlikely to have coma like far by basically 10%. So this is a 10% increase in the distance of coma given by Planck. Okay, so like I would love to take credit like of this DESI, like our measurement is doing anything in this, but actually, like the question is like, can we do like, is there any other way to do this measurement without DESI actually? And the answer for this is yes, we can get to the same results without DESI at all. So what I did actually is I removed DESI from the equation at all. So I took the comma mean redshift, which is like 0.023, and this is mean redshift is coming from DESI comma group catalog. And I checked all reconstruction like that I can get for the Bikov velocity in comma. And you can see here, all of them, if I use all galaxy in comma, and the group catalog in comma, or only the fundamental plane, they are all basically consistent with zero. So because the Bikov velocity error is like 250 kilometers per second, so like all these measurements, like you can say it's consistent with zero, basically. And if you just like use Planck's value of h naught omega m and omega lambda and calculate distance to comma based only on the redshift, on this redshift, and assume zero Bikov velocity, you get something around like 108 plus or minus 4, and this 4 is basically coming from this 250 kilometers per second. So you actually don't need DESI to reach the same results that they found that Planck's will find a higher value of distance to comma or to any other clusters, basically. Okay, just to summarize, so like basically Bikov velocities are good. They are a tracer of the total matter instead of like the galaxy. Galaxy are the only they are only a biased tracer of only the luminous matter, but Bikov velocity is actually unbiased tracers because we can trace luminous and dark matter as well. So you can measure Bikov velocity using distance indicators like Cepheids, type 1a supernovae, Tully-Fisher fundamental plane, or you can use them indirectly using the velocity field reconstruction. And you can apply actually the Bikov velocity can on themselves, they are very interesting. Like some people are interested like to do cosmic cartography. They just like people want to define where do we live, where like where's the next cluster to us. And but also you can do some cosmological parameters like the growth rate of structures. You can measure them with Bikov velocities at very low redshift, and at very low redshift, this is exclusive like region to Bikov velocity. You cannot do this with RSD or anything else. You can do only like growth rate of structure at low redshift using Bikov velocities, and that's where all the like the models actually deviate, and that's where you should measure your growth rate. And Bikov velocity also, like by definition, they can give you a Hubble constant measurement because you have to go through distance if using distance indicators. But not only that, if you measure Bikov velocity, you can help other methods like Cepheids or type 1a supernovae get a better measurement of their H naught. Because you need to correct your redshift for Bikov velocity before doing this. So to summarize all the Bikov velocity survey that we currently have and will have in the future, so we have the 6DF that has been like the gold standard like for over a decade, and that was only 8,000 galaxies, and that goes only to a redshift of 0.06, and that's only in the south. And you have SDSS fundamental plane, and that's very recently like published by Colin Howland and myself. So we published a catalog of 34,000 galaxies, and that goes to a redshift of 0.1. And that's basically in the north. And then we'll have WALLABY, but that will be a Tully-Fisher survey, and that will be using H1 profile, which is a radio, and it will be using spiral galaxy instead of elliptical galaxy, which will be very good in checking systematics between the two measurements. And that goes to 0.07. And our pilot survey is saying that we might get 200,000 galaxies, but there is a maybe here because our pilot survey was very, very deep, and we don't think we'll be able to do the same deep observations for the whole survey. So this number might get like low, but like even half of this number will be great improvement. DESI in the north will be able to give us Tully-Fisher distances and fundamental plane distances. And we actually now have a program for type 1a supernovae as well. And that will go to a redshift of 0.1. And we will get about 186,000 galaxies for this. And finally, in the south, we have a 4HS survey, which is survey on the foremost telescope that will be using fundamental plane, and we'll go to a redshift of 0.1, and we're hoping for this one we'll get about 500,000 galaxy, but that survey still didn't start. And because there is a lot of development happening, so we are actually organizing a conference next year, like in February, like to discuss all this development. So we'll try to cover like everything related to Bikar velocity, from velocity field reconstruction to theory and simulation, and to direct Bikar velocity like fundamental plane of Tully-Fisher. And we'll also have cosmological application like F sigma 8 and H naught. And yes, that's my summary slide.
Thank you. Thank you so much. Very, very nice talk. Adam, you have a question?
Yes, Khaled, can you hear me?
Yes, I can.
Okay. Really nice talk. And I thought your pedagogy was really great. Very, very clear. So the one thing I wanted to ask about was you raised this point, I think I thought, underselling DESI, saying, well, you could have seen the same result on the Hubble constant from coma and its velocity. That's technically true in terms of the value of the Hubble constant, but the significance is quite different. I think actually DESI is actually key in this because, you would predict from the Planck H naught for coma 108 plus or minus 4, and the canonical or consensus distance to coma is like 95 to 100, and so you'd go, it's just maybe 2 sigma high, no big deal. But with DESI, that drops to plus or minus 2. So it's a good factor of 2, and you're at that point you're around 5 sigma for the difference. So what would have been a curiosity or something becomes quite significant evidence, and that only becomes because DESI is tying into the full Hubble flow, and so you really are reducing that error.
Yep. No, I totally agree with you, and I would love to I'd love to have some credit into this, but what I was trying to do here is like to find any other method that we can reach to the same results without DESI, basically. But again, yeah,
The DESI results are not surprising given coma's velocity.
yeah, exactly.
But
Yes,
they're significant in terms of what the significance of the results. So I think DESI gets a lot of credit.
Yep. Thank you.
Thank you. Gagandeep?
Yeah, thank you for the very nice talk. I put it in the chat too. I just wanted to mention a minor point. So you have the set of histograms which show basically different potential systematic terms in your analysis, and yeah, this one. And so there's the last one, which is a fundamental plane analysis with the TRGB calibration. And I think I just wanted to point out, I think this is not just involving TRGB at this point, because the Leo it uses the absolute distance to the Leo group, which is nearby at like 10 megaparsecs, but then it also uses a relative distance between Leo and coma, and that involves quite a few other distance measurements. And so Yeah, I just wanted to point that out. So I think maybe the situation is not as dire because there's a whole lot of extra systematics floating around too.
Yep. So I would like to actually to mention something here. So like from the TRGB, we actually got a lower uncertainty. So we got like a better measurement than SPF. But because of we don't know like how the relative error was, so the relative error like was given actually without any uncertainty. So all the uncertainty was like in the TRGB measurement to Leo, but they said like in the paper that I mentioned in my paper, they said that the distance from Leo to comma, the relative distance, is known to be this. So there were no mention about like any uncertainty associated with that. So that's why we actually, our final measurement in the paper, we actually using the SPF, even if it's associated with a higher uncertainty than the TRGB.
Yeah, and I think I just be clear. I think that's the right move you did. But I think and you know, you pointed out that the big uncertainty there is the relative distance to from
Yeah.
Leo, because
Yep.
you're mixing in like SBF and planetary nebula luminosity function and other things, and so I bet if you went and tabulated those uncertainties, which is probably not an easy thing to do, it's probably very
Yeah.
high.
We were trying actually, and then we said no, like this is really muddy business. So like we'll just take the SPF
Yeah,
for now
it is
until we get a better understanding of this.
But yeah, thank you again. A very nice talk.
Thanks.
Thank you. Indranil?
Hello. I wanted to ask something. So you've obviously managed to tie the value of H naught to the distance to the coma cluster.
Yep.
So what are the prospects for getting a more precise measurements of the distance to the coma cluster, or potentially other clusters, in which case you know the relative distance between that and coma precisely?
Yeah, like so basically we're talking with other people, like, and we have some private communication like with other people who have put some proposals for, and like they got already observation for GWST and TRGB, for GWST and HST, and they got like a lot of TRGB. I think the number that I was giving is about like 40 TRGB and about 200 SPF. And so like we will try to use this in our year one data, but we're waiting for them to put their data public. And so for some clusters, so like I cannot reveal a lot here
Sure.
actually, but some of the clusters actually, so we have about like 40 SPF in one of the cluster that we anchoring to at the moment. We have 40 SPF, and instead of one, we are using here. So for some of the clusters, and we have so many clusters. So our year one will be like much more precise than this.
Okay, thank you.
Thank you. Any other questions or comments? Adam?
Sorry, one follow-up, Khaled, but is there or what would you say is the uncertainty in any, I'm going to say systematic in the fundamental plane between application in coma, which is, you know, a rich cluster, and application in the field?
Yep. Yeah, that's actually a very like good and interesting question, and we were worried like a lot about this. So like in our STSS paper, we found that there is a correlation, there is an actually evolution in the fundamental plane with the richness of the cluster. Or so like if you have ellipticals in the field, they will have a different fundamental, they will sit on a different fundamental plane than like in a cluster, for example. But that's only in STSS. And we didn't see this with other surveys like 6DF, for example. And we think the problem with SDSS is that there is a lot of fiber collisions, and it might be a problem with the survey itself, SDSS, not with the fundamental plane in general. But if we take STCS as the reality, so we'll have like our comma will be like biased. Say our comma calibration will be biased, and STCS is the correct one because comma is very rich cluster, and that means our measurement of H naught is already biased low actually. So
Yeah.
if you use the STCS thing, so like again, so like if it's biased low, if it bias our results low, that means our true results should be 80 or something, which I don't think that's likely. But again, we are testing this like with year one data, and we'll see actually, because here we have only like again one cluster, and basically the SV was batches of the sky, so we don't have a lot of field galaxies to compare with. So in DESI we were not able to do this test, but we did the test with 6DF, and we didn't see that evolution. And we tested it also like with even older surveys and we don't see that evolution. We'd only see this evolution with richness with only STSS.
Thanks.
Thank you. Indranil?
I was wondering, like, can you go to the slide where you showed the that you fixed the Q naught at minus 0.55? Yes. So here, I was wondering if you've done an analysis where you perhaps fix J naught, but you allow both Q naught and H naught to vary.
Yeah, this is interesting actually. So we actually did the analysis without fixing anything.
Mm-hmm.
So like we fit for everything at the same time. We fit for H naught, Q naught, and J naught. But our Q naught was actually unphysical. So we got a very weird value for Q naught.
How much did you get for Q naught?
Well, it was like very, very unphysical. So like it doesn't make any sense. So we got a very like weird. So it was like 3, but we got 3. But the error was like plus or minus 10 or something. But for J naught we got 1, and for H naught we got 70, is very low. But again, so like we actually we couldn't like that's completely different from lambda 3m basically. So if we think that's correct, but our redshift range actually we shouldn't do this test with our redshift range. But what we're doing actually with DESI, we'll try to combine this with supernovae. So combining our fundamental plane with Tully-Fisher will combine actually Tully-Fisher, which is like a lower redshift than fundamental plane, with fundamental plane and with type 1a supernovae, and we'll try to fit for H naught and Q naught and G naught.
So is there not also like a degeneracy between the Q naught and H naught if you do an analysis like you're describing where the Q naught and J naught
There
are
is.
free? So you
There
can
is.
also so you can also get like
Yes.
larger values for more
So,
negative
yeah.
values for Q naught and higher H naught, I suppose.
Yes, so like we did also another test. What we did, so instead like so the prior at the beginning, like when we did this like simultaneous fit, we put the prior to be not informative at all. So we left it like a flat prior, like between minus 10 I think and 10 for Q naught, and
Yeah.
the same for Q naught. So but if we add like a prior, like a very small prior, using the value like for Q naught and G naught, we got the same results here. So we got here. So we got the same results if we put a very, very tight prior, or
Well, that's not
like,
surprising that if you put a tight prior.
yeah, of course. So it is the same thing, yes, as fixing it. Yep.
It's also the same as fixing omega m equals 0.3 and omega lambda equals 0.7, because this redshift range is very narrow. So I suppose you're not really sensitive to the higher order terms.
Yeah, that's what we're mentioning in the paper. So what we said in the paper, we cannot actually like fit for these other parameters. The only thing that we can fit for at the moment is h naught. until
But
we
this
get
brings me on to
more data.
another, like, if I can ask just a quick question. So here, obviously, one reason for this is that the data is limited to redshift 0.1. In the future, what are the prospects for going out to a higher redshift?
Okay. Again, that's a very good question. So like with fundamental plane, with the error that we have now, which is like 23%,
Yeah.
I think going to a higher redshift will be pushing it. But we have another program like using BCGs, which is the brightest cluster galaxies.
Mhm.
And instead of, so like if we put this in the fundamental plane, we can actually decrease the scatter by at least 5%. And it is the same fundamental plane, but using a different type of a galaxy. We're using
So the
only
scatter
the
will be
brightest.
18% instead.
So like it's actually sitting at 18% at the moment. So we think we can push this a little bit further, but that's like 18% is not the only player here. So the second thing is that like because it's very bright galaxies, we can get a volumetric sample, a volume limited sample basically, and we can get a very high signal to noise for these galaxies, given that DESI is doing bright BSG like bright galaxy survey and doing also LRG survey. And if you combine both of them, we can get a volume limited sample for BCGs.
And how
So
far
we'll
out
have,
do you... Go ahead.
so like okay, so like I was testing this actually this morning with a student, and we think we might be able to go to 0.3. So we at least we have the signal to noise to go to 0.3 with BCG. But this is we're still testing this.
Yeah.
We don't know like if we'll so but yeah, like for in terms of like signal to noise, so we can get a good signal to noise until 0.3.
Thanks. Yeah, good luck with that.
Thank you.
So let's thank Khaled again.
Thank you very much.